Universal approximation theorem, or UAT, is essentially a single layer neural network that can approximate a continuous function. And here we can see to the left over here, this is a continuous function that I grabbed from the website, and UAT is really cool because it explains, according to Andre Yez, why neural networks behave so intelligently. And we'll dive into that a little bit more, and we'll understand Andre's quote a little more thoroughly. So the main point behind UAT allows for a simple linear relationship to exist between inputs and outputs. So it can take large, complex functions and breaks them down into really tiny linear dividends, essentially. And each one of these bits are taken in by a neuron, and that is taken in one by one. So each little tiny thing that's broken down from that massive, huge, complex function, each little chunk that gets divided up gets fed to a neuron individually. Okay, so here we can see our binary step function and a nice little diagram that I found for it, found in the link below. It's the simplest, most basic building block of activation functions, where the neuron gets activated when the input crosses a certain threshold. So if f of x is 1 here in this specific situation based on the diagram, that surpasses the threshold. And if we were to set f of x less than or equal to the threshold, then it would be equal to 0. Building block neurons here is another cool visual, and we'll get a zoom in on it on the next slide. But real quick before we do that, combining them creates building blocks. I think we already touched base on that. And a step function is the neuron number 1. We take that output from it and we subtract neuron 2's step function output from it. And that's how we create a step function between 1 and 2. And that's given that 2 has a different activation bias. Because if they were the same, then it wouldn't really get us a step, because their differences wouldn't exist. They wouldn't have a difference. So, and it creates a little step or a pulse that we can see right here. And yeah, the weights rely on it as well. And here, this example specifically is a flat line because the last pairs cancel out. Functions are approximated through adding the different possible combinations of each step function. And that creates a piecewise function of constants. And again, that's an approximation. And we have to keep in mind that the activation function must be, again, continuous, non-constant, and bounded.